Good, good, good. Yeah.
Are you familiar with the by any chance?
No. Okay. Okay. Lecture 16.
Yeah. I'm very glad. Yeah,
Okay. Actually, before I start, I'd like to talk about the mid-session test. So first, mid-term test. Okay, so first thing, in person only. There are no other options. So you basically are here or you're not here. If you're not here and you have not applied for special consideration before the test, you get 0. No further discussion entered into. So in person only, and it's Friday, 17th, in room 32, i.e. here, at 10 a.m. Okay? So it's in this room live. It's 50 minutes. Okay? And you will have a formula sheet. The formula sheet is identical to the one that is on additional notes. On Moodle. So there's a section of additional notes from me. There's a formula sheet in there which says mid-session test 2020. It's identical to that. I just copied it. It's the same. So what do I cover? All classical thermodynamics. Why not? You're about to do statistical mechanics, so this is lectures 1 to 13 inclusive, as defined by notes on Moodle. So these scribbly sheets that I have saying lecture 1, lecture 2, lecture 3, that's them, okay? So that's the test. The test has not been written yet. I'm Mr. Last Minute, like you guys probably are as well. So it doesn't exist. You can't ask me what's on it now. I don't know. So probably 2 questions. Multi-part. Okay, so what I will include. 1, you'll be given a cycle and you need to derive equations for Q, work, energy, entropy, etc. for the cycle or any part of the cycle. You need to be able to derive equation for efficiency. Perfect. You need to be able to plot PV and or TS diagrams, etc. So basically, one thermodynamic cycle, you need to be able to calculate anything for it. If you look at my past mid-session tests, they're all online. There's always a cycle there. You can actually go through and find out what my pattern is, what year I ask which one, but you'll see there's about 20 of them. If you can actually solve them all, you'll get 100% in the mid-session test, okay? So it's not a big deal. No, talk to the tutor if they've got something. There's a lot of them are straight from the notes. I mean, I think I've calculated work for isobaric, isochoric, isothermal, and adiabatic. They're all made up of those. So you can get all the works, all the heats, all the entropies. We've done them all. So all you've got to do is piece it together. Okay, you've got to understand a fundamental equation. So either USVN or the other one, and first order homogeneous. And you need to be able to derive stuff from this. Okay, so all the kind of things we've done, you need to be able to figure out what does this mean? What are the consequences? 3, you need to know the toy systems. So the ideal gas, Van der Waals gas, and magnetic system. Okay, the stuff we've done for those, you need to have some sense of it. You need to be able to calculate entropy for irreversible process, as we've done a few examples of that. Probably I will ask you about concepts, processes, equilibrium, what this business dq means, dw, etc. And 6, you need to know Carnot. The cycle, theorem, etc. So that's what's going to be in it. It's not going to be all of those things. I will pick things, but I will try not to pick obscure and trivial things. I'm not going to ask you weird questions about magnetic systems or magnetic equations of state. I'm not going to have a thermodynamic cycle for magnetic system because we've barely touched on it, okay? It's going to be, I want to know what you know, not what you don't know. Okay, so what else can I say about it? The exam is closed book. No devices whatsoever. So no phones, no calculator, no anything, no notes, no books, nothing. Okay, so what you need is a couple of reliable pens, pencils, eraser, ruler if you want. That's all you can bring into the exam. No. Okay, so Let me underline it. No devices whatsoever. No calculators. Okay? I'm not going to ask you to work out things of numbers. I assume you can multiply. And I assume that if you can't multiply, you can do this. As a joke, I've almost thought about giving you dead calculators so you can feel comfortable with them. Or a phone that doesn't work, an old Nokia, so you can feel not too nervous. Any questions on any of that? Yeah. No Maxwell's relations. No thermodynamic potentials, I think, because we really did that at lightning speed, okay? So I'm not interested in details. I'm interested in fundamental understanding. How well do you understand entropy? That's going to be kind of a question, but it's not going to be asked like that. Other questions?
When you say those things aren't tested, is it just not tested?
Final exam is going to be similar. Closed book, no this, no that. So basically you come into a room, you'll throw your bags somewhere around there, wander there with pens, ruler, eraser, nothing else. And then you'll get an exam paper, a script you will write. Oh, please write as legibly as possible. I have no tolerance for illegible writing, even though mine is illegible. If I can't read it, I'm not going to struggle with it. If I can't read it, it's 0. Usually it's not a problem, but I have had some students who cannot write at all, and it's impossible. Okay, please use equations. Please use diagrams. I'm lazy, so if I see a diagram that says you fully understand something, well, why should I read all the stuff you've written? Full marks, go on. Okay, I'm going to have to mark a bunch of papers. If I can see clear evidence, you know what it's about, an equation. So with equations, I always want you to derive an equation. I'll use the word derive. That does not mean look up the formula sheet and write it down. That's worth 0, okay? I also mark very black and white. You either get the mark or you don't get the mark. To compensate for that, I use lots of little marks so that it's not all or nothing, but for every step, it's all or nothing, okay? And if it says derive, I mean derive. So you have to show some form of working or justification for the steps you have. Any questions? Any chat questions? Did he say Maxwell relations are not tested, okay? Maxwell relations. I didn't even cover them. They're actually quite easy. If you write down the formula for potentials, differentiate them, they just pop out. It's beautiful. Didn't have time. Yes. I doubt it. We're going to run into them today. In the final exam, though, toy spin system is in. Okay, the equations have stayed not, but the toy spin system is in. Okay, but for this, I think we've hardly done anything with it. But we are doing it today, and we have done it a couple of days ago. But that's not in this test. That's in the final. Happy? It will be tight. You will be tight on time. If you know your stuff, you'll be able to answer all the questions. If you don't know your stuff, you will struggle because it's 50 minutes. 50 minutes will fly. Okay, enough. Any other questions out here? Remember, no Zoom, no online. Okay, so entropy equations. So we now know what entropy is. S equals K, the Boltzmann constant, ln number of microstates. That's the magic equation. Okay, so it means I can calculate S for any system. All I need to do is to enumerate the microstates. And this links microscopic to macroscopic. Okay. And basically this allows me to derive the fundamental equation in entropy form. S U, V, N, okay, for any system. Effectively, it means that the second law is probabilistic. So as long as the numbers are big, the second law is absolute. Once your numbers get very small, like nanoscale systems, entropy can go up or down. But if you wait long enough, it has to go up, okay? It's probabilistic, but you have fluctuations. Okay, let's do it. So entropy for an ideal gas. I think it's monatomic. Okay. So, whoops. Come on, pen. So back in lecture 14, we didn't finish it, and I'm not going to. Lecture 14, I didn't finish it. But see notes. It's a tedious derivation, and you will do something like it again with Julian. But we already did it earlier. We derived this tetrode-Sakura equation directly from our formalism, the thermodynamic formalism. You get this V on N, U on N to the 3 on 2, so it's monatomic. And then you get a constant term, 3 on 2, Kn, 5 on 3, plus ln 4 pi, the mass, divided by 2h squared. So not h bar, but h. Okay, this is the tetrode-Sakura. Sorry, spelling is going out the door. Sakura tetrode equation. Okay, so this is my fundamental equation. This is S as a function of U, V, and N, okay? This is my fundamental equation. I have it because I can derive it from statistical mechanics. So what do? Check. Ln 4 pi mass of the particle to h squared. So m, let me just scribble that. M equals particle mass. And h equals Heisenberg. Okay, so it's semi-quantum mechanical. And I think I'm missing a bracket. Yeah, good, that's it. Check that it's first order homogeneous. And basically, i.e. what you want to get is that lambda s is equal to s lambda u, lambda v, lambda n. Okay, so I'm going to leave that for homework. Check. Yeah, a Planck's constant, sorry. And it's yes. Okay, so if you look at it, every time anything appears in that equation, it's divided by n. So if you multiply v by n and lambda by n, they cancel out. So it has that property. Planck's. Okay, so now I want to derive the equations of state. Okay, now given that we integrated this a long time ago, integrated the equations of state and derived tetrode-Sakura, obviously it's going to spit them back. So, number one, 1 over temperature equals, or defined as, the entropy du, keeping V and N constant. So if I do that, I just differentiate d du, keeping V and N constant, of that equation, okay? I'm not going to write it. Okay, so do it yourself, homework. And if you do that, what you end up with is 3 on 2 K N on U, okay? And this gives me U equals 3 on 2 KT NT. Okay? So that's one. I get that one. The second one, 2. I can write that P on T is equal to the derivative of the entropy with respect to volume, keeping energy and N fixed. Homework. Show that you get PV equals NKT. Please do it. I will do the third one because we've never had an equation for the entropy, for the chemical potential of an ideal gas. Let's do that one. 3. So 3 is that minus the chemical potential on T is defined as the entropy, the number of particles, constant energy, constant volume. Okay, so let's multiply that out. That's ddn, partial derivative, U and V constant of, I'll write it this time, N, K ln of V on N, U on N to the 3 on 2, plus some constant. So I'm differentiating with respect to N. I've pulled the N out the front here. So the second term is just a constant. So irrelevant when I'm differentiating. So if I differentiate this, I guess this is equal to the entropy divided by N plus NK ddn of ln V on N, U on N to the 3 on 2. So if I differentiate this through, I end up with entropy on N minus 5 on 2 K. Okay, looks stupid. So what this spits out is that my chemical potential for a monatomic ideal gas is equal to 5 on 2 KT minus S on NT. So for this monatomic ideal gas, this chemical potential is intimately linked with the entropy, okay? And this number is large and negative under classical conditions, i.e. where quantum mechanics does not play into. Yes. Say again. Volume. It's vanished. It's not there. Disappeared. Yeah. Because when I differentiate this thing up here, when I differentiate this part here is entropy. Go away. Go away. Entropy over N. And I just differentiate it, okay? And so I get firstly differentiate with respect to n, the n goes away and leaves mu of entropy over n. There it is. And then I differentiate this stuff with respect to the n and multiply by n. So all I'm doing is using product rule. Okay? So there it is. We finally see it. Okay, so now I go to the spin system. Okay, good. Any questions about that? So this stuff is more fun. Entropy of ideal spin system. Okay, so this is my toy model number 2. And from lecture 13, this one we did do. We got that S, it's a horrible equation. K ln. The way you understand this equation is you break it up. 2 pi n over horrible stuff, 1 plus pi n squared minus pi squared u over mu b squared, all that to the half. Okay, that's ugly. Plus nk ln n. But the magic happens from these two terms, minus n on 2 minus the energy on 2 mu b. That's the steps in energy as spins flip. K ln the same thing, n on 2 minus u on 2 mu b. Then I get another term which is exactly the same, but I have plus signs. Plus u on 2 mu b. That's it. Okay, when I look at that, I scream. But the bit that's interesting is this stuff. Okay? So, what happens at energy equals 0? Well, at energy equals 0, you have n on 2 spins are up and n on 2 spins down. And I can derive some stuff on that. So let me do that on a separate sheet. So at u equals 0, this is my maximum, okay, my maximum value. I have S is equal to K ln that first term, 1 plus 2 pi n over 1 plus pi n squared, all that to a half. I've still got the n k ln n term, but now I have minus n on 2 k ln n on 2 minus n on 2 k ln n on 2. So what's happened is those second terms, in terms of u divided by 2 mu b, the energy broken into steps have vanished, all gone. So I can write this again as k logarithm or bracket ln this ugly term to the half. That's that guy. If I was smart, I'd just move it to there, but I'm not that smart. And this stuff over here is just equal to plus n k ln 2. Okay? Inside the logarithm, I'm pretty sure. Let's go back and check. square root is inside the logarithm. Okay, so if you want, I can put that. Okay, this thing here simplifies. I put the k out the front. So that k is gone. It's out the front there. So I simplify this. This is approximately equal to ln k, sorry, bad writing, k natural logarithm of 1 over square root of pi n on 2 to the n. So this 2 to the n is that guy going to there, going into the logarithm. So basically, I convert that to 2 to the power of n, and I'm adding 2 logarithms, so I multiply and put it inside. So this gives me that the number of microstates at energy equals 0 is of the order of 1 over square root pi n on 2 to the power of n. Okay, that's what I want to get from that. Yeah. Say again? Simplifying this messy equation. That's where I got that from. Okay. Yeah, I'm just simplifying that equation and I'm making approximations that 1 is small compared to n. Okay. So it's 1 plus pi n, that's disappearing. And 1 plus 2 pi n, that's disappearing. So I end up with that instead. Well, n is a large number. So 1 plus a large number is a large number. So that's all I've done there. Okay, so now I want the equations of state. Okay, so it's the same old game. I can write 1 over temperature is defined as ds du, constant v and n. Okay, so I differentiate. S, in this time it's U, N, and the magnetic field, B, or the B field. And I'm going to ignore first term. Okay, and if I do that, the derivative is not too complicated. I get, keep it there, purple, make it blue. I get 1 over temperature is equal to K over 2 mu B. That's my step in energy. Logarithm of N mu B minus U over N mu B plus U. So this is coming from those two terms that have, one has plus energy, one has minus energy. And if I rewrite that, I need to do some mathematics. I get that U, the energy, is minus N mu B. And then something that looks horrible, but really isn't. E to the plus mu B over KT minus E to the minus mu B over KT divided by E to the plus mu B over KT plus E to the minus mu B over KT. Anyone recognize that? Okay, you don't have to recognize it, but what kind of a function is it? It's a, it's a hyperbolic. It's a trig function, but a hyperbolic trig function. So that is fan, if that's how you wish to pronounce it. U is equal to minus n mu b, hyperbolic tangent, mu b over kt. So these kind of functions appear everywhere. Somewhere you need to have a table that has the hyperbolic trig functions, the ordinary trig functions, are all written in this kind of notation. They're all going to change by where the pluses and minuses sit and whether they're complex or real. But that's that one. Okay, so that's my thing. So now I can actually simplify again. The one that we derived, wag back, bang, bang, that guy, and I'm ignoring the first term, okay? So it's basically coming from the green stuff. Those two terms are dominating, and I'm differentiating with respect to u, so this nk log n does nothing. The properties are based on those in the green bracket when I do the derivative, okay? That's where that function has come from. Honestly, I haven't thought about magnetism for a long time. I think it's small compared to those two terms, so it's just fallen out. Okay, so I've got this equation. Now I can add some simplifications for high T and modest B, i.e. what I mean is mu B is very much less than KT. Then if I do that, my hyperbolic tangent X is approximately X. So if I do this, I get my energy is equal to approximate, let me fix that, approximately equal to minus n mu squared v squared over kt. Okay, but we know that the energy is equal to minus the magnetization of the material times B, where this is the magnetic moment of my system. Okay, so if I do that, I get that M, the magnetization per unit volume, is the net magnetization divided by volume, is equal to N mu squared mu naught H VKT. And I'm using that B is approximately mu naught H. And this is just equivalent to Curry's law. Okay. And it tells me what the Curry constant is. It implies that the Curry constant C is equal to N mu squared mu naught over V K Boltzmann. Okay. So that is one of my equations of state, and it popped out just from this. Yeah. Yeah. Good. M equals, M is the total magnetization for the material, the total magnetic moment. And I usually write it as normal M, not script M, which is magnetization per unit volume. That's all. Okay, I can talk about sharpness of the peak, but I want to skip to something else. So I want to get to the end where I want to get to. So sharpness of peak C notes. Okay, so go and C notes. I'll skip that. Okay, let me now look at this in a different way. Entropy for ideal spin system. So you've got to remember this is a toy system, and it's going to have some toy properties that are cool, but you have to be aware that they're toy, so you have to be careful. Okay, I'm going to write the entropy out again with feeling. S is equal to K times a half ln some horrible stuff, 1 plus 2 pi n over 1 plus pi n squared minus pi squared u over mu b squared, all of that, plus this silly term, n ln n, yep, then the two nice terms, minus n on 2 minus u on 2 mu b, ln the same term, n on 2 minus u on 2 mu b, minus n on 2 plus u on 2 mu b, ln n on 2 plus u on 2 mu b. Okay. Then I can say for u equals 0, I've got n on 2 spins up and n on 2 spins down with respect to my B field. And what I get is that S for u equals 0 is equal to K ln the first term just reduces to 1 plus 2 pi n over 1 plus pi n squared. Give me a sec, I gotta think. Yes, hang on. This to a half. Okay, there was a half out the front. I've popped the half up to there. Okay, times 2n. We derived this before, sorry. And this is S max. Homework, prove. Okay, prove that that's a maximum. So it's a peak at that value. Yes. Whole thing. Sorry, missing bracket. Actually, K multiplies everything. Correct, missing bracket.
Also, for the first form, there's no square root effect.
The square root comes from this.
All right.
Half
Yeah.
goes into there. That's all I've done is pull it into there. That's all. Okay, so that's what's happening there. But what happens at two extremes? What happens if I have the two extreme energies, all spins aligned or all spins anti-aligned? What's the entropy? 0. Okay. So if I have all spins aligned, I have only one microstate. Let me write that down. So I can write that all spins up implies that total energy is minus n mu b. And all spins are down, anti-parallel to B, implies U equals plus n mu B. And for each of these, both have one microstate. And this implies that S equals 0. Okay? So this is weird. So let me write that down, that the entropy when U is equal to plus or minus n mu B equals 0. Okay, so now make a graph. Okay, so in the middle, I've got energy 0. Half spins up, half spins down. At the bottom here, I've got minus n mu B. All spins aligned with the B field. Over here, I've got plus n mu B. So in the middle, I get my maximum entropy. Over here, I get S equals 0, and over here, I get S equals 0. And if I join up the dots, okay, what is wrong with this? Entropy is going down with energy, okay? Is that allowed? Okay, let's think about it for a bit. Let's replot it. What about temperature? Yep, let's do it. So I can write that the S du equals 1 on T by definition. Or I can rewrite that as the ln omega du Vn fixed is equal to 1 on Kt, which is my temperature parameter. Okay, so you'll see this guy again. So first I just plot my temperature parameter, and that one is an easy plot. I get, I'll take up the whole board here. This is now beta, my temperature parameter, versus U. And here I've got a 0 slope at 0. Here I've got minus n mu B plus n mu B. I'm going to draw a dotted line there, dotted line there. And if I plot this function, I get something that goes off to infinity, comes down here, goes flat. Well, I've drawn this badly, goes through there and down there. Okay, so this is beta is equal to 1 on Kt. Okay, so I've got that, but what I really want is temperature. So now I plot temperature. Oops, go away. Temperature, oh, go away, go away. Temperature as a function of energy. Okay, so now instead I put my dotted line at the origin. And now what happens is my temperature here at minus n mu B is 0. because that was, the slope was, the inverse of the slope is 0. And this now goes up to there, and comes back there and does that. It goes to 0 at plus n mu b. Wow, that is strange. So, for u such that minus n mu b is less than or equal to u is less than or equal to 0, temperature increases from 0 to plus infinity, okay? So T goes to infinity is equivalent to half spins up and half spins down. Okay? And T equals 0, all spins parallel to B. Okay, so this is for that condition. Okay? And this gives me S equals 0. Omega equals 1 at energy is equal to minus n mu b. So that side's okay, yeah. Yes. Okay, this is why I want to save this to last. Okay, so for energy greater than 0, okay? So I've got a lot of weird things happening here. More spins in high energy, higher energy. In high energy anti-parallel orientation. Okay? So what does this mean? It means that my negative temperature is a population inversion. Okay, so I've got more spins in the high energy state than in the lower energy state. Have you heard of this before? Population inversion. Nobody. Yeah, what? Have not. Okay. Lasers, that's how they work. You create a population inversion. It's far from equilibrium. You flip things. So this is a high energy configuration. So believe it or not, negative temperatures are very hot. If you had such a temperature inversion, don't stick your hand on it. It's going to burn you, okay? So it has more energy than U equals 0 when T was going to infinity, okay? So it's got more energy than this situation, okay? So normally this system is far from equilibrium, okay? Unless completely isolated. Okay, so if this system was in contact with anything else, including internal vibrational modes or anything else, it would dump energy into them and the population inversion would revert to a normal Boltzmann distribution. Okay? Yeah. Kelvin. Okay, same. So let me add some things to this. Cannot move. from positive to negative T by passing through 0. Zero, okay? 0 Kelvin. So, question for you guys. Why does this happen? So I want you to think about it. Entropy is log of number of microstates. What is special about this system? Nope. As energy increases, basically as energy increases, the microstates increase. And then you pass a certain point, they start to decrease. Why is that? And why does this not happen for ideal gas or pretty much any real system? What's the difference about this system? If you took an atomic system and you had all these atoms in the ground state, and you start dumping energy in, they get excited, excited, excited. If you dump in more energy, what happens next? Well, they get more excited, and fly off. But in this case, they can't. The spin can be up or down. That's it. We put a restriction on it. It's a toy system. Okay? So this system is bounded. There is an absolute maximum energy you can dump into it. After that, the energy stops because all spins are flipped. So why has this happened? It's because we have a bounded system. What is that? Oh, wrong one. Because system bounded. Okay, so where U strictly has to be less than U max, which is where all spins anti-parallel. Okay, so U max equals plus N mu B. So this is a really peculiar case, okay? And as somebody said, in a laser, this is exactly what you do. In an NMR experiment, this is exactly what you do. And so you're creating these population inversions where the temperature is negative. They are very hot. They want to get rid of that energy, but it's negative temperature. So if they are coupled in any way to anything else, including some other modes in the system, they will dump the energy. Okay, they can't hold it. So in reality, you can do this in a bounded system on a time scale at which it exchanges energy with some other outside system. But all other types of systems are not bounded in energy. Therefore, you do not get negative temperatures. Okay? So it's a peculiarity. This is why I like this toy system. It likes you to prod meaning of things. Okay, that's it for me. It's Julian on Monday. Julian will be fun, I guarantee. He's really good. And he will take you through statistical mechanics properly, picking up from where I left off, which was Boltzmann's equation. Okay, have fun. And if you have questions, pester me before Friday. Friday is the mid-session. And you can pester me after that because you'll have an exam at the end. Good luck, do well. Okay. Good.
Thanks.
Sure. Good, good. Me, excellent. Let me walk out of the room, but let me just shut these things down.